Imagine pointing a telescope past the orbit of Mars and watching a speck that should creep, drift, nudge its way across the star field, only it doesn't. Frame after frame, it appears fixed, as if the sky itself has clipped it to the same coordinates. And the first question that slams into every trained mind is simple and terrifying. How can anything in a gravitational universe just stop? That's the spark behind tonight's investigation. Not a headline, not a rumor we swallow whole, but a chain of observations and claims that lit up professional listservs and late-night Slack channels from Hawaii to Chile, a candidate interstellar object, informally nicknamed 3I/8less, reportedly held position against background stars for hours, then nights, defying predictions that had it on a clean hyperbolic escape. The name matters. 3, I would mark it as the third confirmed interstellar object after Oumuamua in 2017 and Borisov in 2019. And Atlas nods to the survey work that flags fast movers beyond a routine Mars flyby pace. But the confirmation is the point, and tonight we track what is known, what is contested, and what is pure speculation, dressed in technical language. Here's what pulls us in automated pipelines at Pan-STARRS in Hawaii, flag a faint source barely above noise that initially fits the profile of a long-period comet or an interstellar object on a wide hyperbolic path, nothing unprecedented. Spectra reportedly show ordinary cometary volatiles and dust signatures, brightness evolution, looks textbook trajectory fits, are stable. Then, a jolt cross-checks from observatories in Chile, Spain, and South Africa circulate, showing negligible motion between nights smaller than a fraction of a pixel, smaller than the astrometric jitter you expect from seeing changes. In the raw narrative, that's when NASA data delay starts trending in private chats, not because the agency is hiding anything, but because every serious team pauses, re-reduces, and sits on preliminary numbers until clocks mounts detectors and calibration stars are audited to death. That caution is not a conspiracy. It is how you avoid turning instrument drift into front-page physics. Which brings us to the central question of Part 1, if the sky reports no drift. What must be true for that to be real, and what must be false in the chain of measurement if it isn't, before we even whisper new physics? We test the old timing offsets between observatories, mistagged reference catalogs, atmospheric dispersion that smears a point source asymmetrically, tracking rates set to the wrong sidereal standard centroid bias when a faint source overlaps a background star, and the most treacherous of all selection effects, where analysts prefer frames that appear consistent and unconsciously downweight the outliers. On the record, the only historically secure facts are these: Oumuamua was discovered in October 2017 and showed a non-gravitational acceleration consistent controversially with outgassing. Borisov, discovered in 2019, behaved like a normal comet. Pan-STARRS and Atlas are real survey systems that catch faint movers. And nothing in classical celestial mechanics supports a macroscopic body stopping against inertial space. Everything else in this case file is a claim we will interrogate. But we also owe you the reason this story captured professionals who normally roll their eyes at sensationalism. If an interstellar object really did exhibit apparent standstill even briefly, there are testable non-magical pathways to mimic that effect. Gravitational lensing under a razor-thin alignment, a transient magneto-hydrodynamic pocket in the solar wind that retards charged dust emission and scrambles the centroid or a geometry where outgassing thrust cancels plane of sky motion while the object still moves along our line of sight. None of these are easy. All of them leave fingerprints in spectrophotometry or timing, and that is where our investigation goes next. Our tone tonight is neutral, investigative, but we're not afraid to ask heated questions, because this is how science actually progresses: a stubborn anomaly, a brutal audit, a better model, or a public correction. Keep those 5 phrases in your head as we proceed. 3I/8less interstellar object, Mars flyby, NASA data delay, and yes, the green flash we'll explain later when we talk about transient photometric spikes near horizon imaging, because, by the end, you should have enough to argue your own verdict. For now, hold the headline in your mind's eye: a speck that should move doesn't. A discipline built on motion, stunned. What would it mean if the stillness were real? What would it expose if it were only in our instruments? The first phase of the investigation inside NASA's Jet Propulsion Laboratory was quiet. Almost clinical teams were assigned to replicate the anomaly from raw data running independent pipelines on the same images that showed 3I/8LES apparently frozen beyond the orbit of Mars. The methodology was straightforward. Align frames measure the centroid shift relative to fixed background stars and compare that motion against known parallax and predicted orbital drift. What came back was unsettling. Across instruments on 3 continents, the apparent offset was statistically indistinguishable from zero. A cosmic coincidence? Possibly. But zero in astronomy is never really zero. It means the motion was below detection thresholds, a statement about sensitivity, not stillness. The first technical report, leaked through an internal memo, proposed that thermal noise combined with background star interference might have masked real movement. Others pointed to variable atmospheric seeing conditions that can cancel out drift vectors when averaged across stacked exposures. Yet, as recalibrations poured in, none of those explanations fit neatly. The coordinates remained the same night after night, as if 3I/Atlas had parked itself in the void. Observers remembered that every confirmed interstellar object has followed a hyperbolic trajectory. Oumuamua came in at 26 kilometers per s relative to the Sun Borisov at nearly 33, and physics dictates that no object unbound to solar gravity can simply halt. To freeze it would have to lose momentum equivalent to billions of tons of kinetic energy, something even the most violent outgassing cannot provide. That's when the first active braking theory appeared. Maybe a massive jet of volatile gas erupted backward, counteracting forward velocity like a rocket thruster. On paper, it's not absurd. Comets vent asymmetrically all the time. But calculations demolished the idea. To nullify a velocity of tens of kilometers per second, that jet would have to sustain thrust for hours, precisely aligned with the motion vector without imparting spin. No recorded comet has ever shown that level of precision or energy. The second wave of models explored external forces. Could a magnetic trap in the solar wind, a region of balanced magnetic tension, momentarily suspend a body rich in metallic compounds? Plasma physicists argued the fields were far too weak. At that distance, microtesla forces cannot stop a mountain of rock and ice. So the attention shifted to optical illusions, gravitational lensing diffraction effects, or line-of-sight coincidences that make a moving body appear stationary if it passes behind a dense field of stars. The mathematics behind those illusions demand precision alignments measured in arcseconds, but they are physically allowed. In fact, if 3I/8LES happened to cross a tiny region where the curvature of space-time bent its reflected light around a background star, the composite centroid could momentarily appear frozen. It would be a triumph of geometry, not a break in physics. Yet the data lacked the hallmark distortion, no duplicated arcs, no magnification spikes. In short, every classical explanation had cracks. Inside the team's morale split. Some leaned toward statistical fluke. Others whispered that the numbers were too clean to dismiss. The deeper question was psychological. How many times do we rewrite calibration code before admitting that, maybe just maybe, we are glimpsing a frontier we don't yet recognize? The debate and the turning point. 600 words. By the third week, what began as a quiet technical issue had become a storm inside the astrophysics community. Private channels filled with competing hypotheses, and every major observatory wanted a piece of the data. One group at the Goddard Space Flight Center ran magnetohydrodynamic simulations showing that under extremely rare conditions, the solar wind could fold back on itself, forming a stagnation pocket where magnetic and plasma pressures cancel out. If 3I/Atlas, with its metallic inclusions of nickel and cobalt, drifted into such a pocket, it might have experienced a temporary equilibrium, a literal standstill between opposing forces. Elegant, yes, but the math failed to match the observed stability. The solar wind's chaotic turbulence would rip apart any such pocket in minutes, not days. Others in Europe revived the lensing theory, arguing that we might not be seeing the object's true position at all. Perhaps its image had been gravitationally refracted by a compact mass, an asteroid, a dead star, or a density ripple in interstellar plasma. This too was possible, but improbable. The necessary alignment would have to be exact, to within fractions of an arcsecond, a coincidence so perfect it bordered on fantasy. As theories fell apart, a more unsettling idea took hold. What if the object wasn't behaving passively? Some researchers dared to compare 3I/Atlas with Oumuamua, whose unexplained acceleration in 2017 had been brushed off as outgassing, despite a lack of coma or dust tail. If two interstellar visitors showed anomalous motion, could there be a shared property material composition, internal energy dynamics, or even an unknown structural mechanism that set them apart from ordinary comets? Officially, NASA avoided such speculation, but off the record, scientists admitted the coincidence was unnerving. At JPL, a small interdisciplinary group was formed to re-examine the raw light curves looking for periodic fluctuations that might indicate internal processes. That's when something new emerged, a subtle thermal oscillation repeating every few hours. It wasn't random noise, it had rhythm, a measurable pulse in infrared wavelengths, like a system regulating energy. The amplitude was small but consistent across multiple telescopes. No known natural process at that distance from the Sun could produce such stability. The data were published quietly in an internal bulletin labeled Pending Confirmation. Outside NASA, the speculation turned feverish. Could it be an automated response? A self-correcting feedback from deep inside the object. Most dismissed that as science fiction, but it raised a provocative scientific point. Interstellar material could have formed under conditions unknown to our solar chemistry, leading to behaviors we don't yet have models for. Some compared it to quantum interference at a macroscopic scale, where the object's reflected light oscillated between red and blue shifts as if its velocity vector existed in multiple states at once. That interpretation was extreme, but not meaningless. In the quantum domain, superposition is routine. Applying it to celestial bodies sounded absurd, yet it captured a core truth: observation limits perception. A few voices proposed that the apparent standstill might not be physical at all, but the effect of our frame of reference, a complex interplay of relative velocities, gravitational gradients, and temporal distortions near the Sun's heliopause region. That would make 3I/Atlas not a defiance of physics, but a mirror exposing the complexity of motion itself. By this point, 3I/Atlas had become shorthand for a philosophical riddle wrapped in telemetry, an interstellar object that made even seasoned physicists doubt the ground under Newton's laws. And somewhere behind the math and memos lingered a human feeling too uncomfortable to quantify the fear that our instruments might, for a heartbeat, have glimpsed something real and unreachable, a pause in the universe's endless drift. The aftermath, and the question 500 words. Weeks later, a single update slipped through the noise. 3I/Atlas had resumed motion. The coordinates shifted again faintly at first, then steadily its trajectory, returning to a hyperbolic arc that led outward, back to the interstellar dark. Relief spread through control rooms. The laws of motion were intact, at least on paper. Yet, the data from those still nights remained intact too, and no correction, no instrument error could erase what had been recorded. NASA's official position framed it as an unresolved anomaly, a transient phase likely caused by measurement uncertainty or unmodeled photometric distortion. Behind that diplomatic phrasing was the unspoken truth: nobody fully understood what had happened. The anomaly forced subtle changes. Search algorithms in automated sky surveys were rewritten to flag not only objects that moved, but also those that seemed not to move at all, an admission that stillness, once dismissed as background noise, might be just as significant as motion. In think tanks and conferences, scientists began to speak of dynamic null zones, hypothetical regions where radiation pressure, magnetic tension, and gravity briefly cancel, producing a field of zero net acceleration. It was an abstract fix, but it offered a language to contain the event without invoking impossibilities. Beyond the science, something else shifted. For a generation raised to believe that the cosmos is perpetual motion, 3I/Atlas represented a pause button on existence, a reminder that even in a universe of laws and constants, perception can fail, and silence can be data. The interstellar visitor left no tail, no debris, no definitive clue, only a question. If an object from beyond our sun can appear to stop, even for a heartbeat, What else in the night sky might be waiting perfectly still until we learn how to see it?